Okay, welcome back. Sorry, I'm a couple of minutes late with the lecture. You ready? I want to make an announcement again about the clicking roundup numbers. I posted over the weekend. Actually, I think I posted on Thursday or Friday. Everybody's got a number in their grades page. It looks something like this. Something, something, point, something, something. Right now, so this is a typical example, 16.19. And what this means is this is your clicking roundup number. And it means that you've got 19 out of 23. Right now for this class, as of Thursday, the baseline number of questions was 23. Now after today, we got about another 3 or 4 questions going, so it'll change. But for right now, as of Thursday, it was 23. So this student has 19 out of 23 answered. That's pretty good. And they also have 16 out of 23 correct. So when you're looking at your grades page, you can always think, okay, that number encodes 2 different subtotals. How many correct and how many you've actually answered. Now the class participation, part of your grade, 25 out of 25, comes out of the decimal, the hundredths and the tenth place decimal part of that figure. We worked on that last time. All right, so that's up there now. Any questions from the floor? Yes?
I'm 17.2.
Dude, don't tell people you just violated your own privacy. Now, if a student that happens to have something, something, point 2, what that means is, you know how Canvas screws, this is too hot. Let me pot this down a little. You know how Canvas screws around with zeros? Like when you're typing in a calculation, it puts zeros in. Same thing here. It takes that 0 out, so it's supposed to be a 2-0. Okay, so if you have a 0.1 or a 0.2 right now, that means 0.20 and 0.10. So, and these numbers will change. I'll probably do another roundup in a couple weeks. Like maybe right after exam 2. So you can kind of see. And, the nice thing about exam 2 is after exam 2, after the grades are posted for it, you'll have everything in place to figure out your grade going into the final. In other words, you'll have 2 midterms, and you'll have a bunch of homework that you can convert to something out of 25, and you'll have a bunch of clicking that you can convert to something out of 25. So you can just start to get in the habit of doing that. But of course, we'll have a third exam, but then after the third exam, we drop your lowest and keep your best. So you still have 2 midterms after the third exam. So once we get to October 16th, our second midterm, then you'll just be able to start cruising. All right, questions about any of that? Yes. Wait a minute now. What's going on here? You're sitting over there instead of over here. I don't know. It's you just. I just want you to know I'm alert. I see everything. The correct goes to a bonus at the end of the semester. All right. The decimal part is your participation number. All right. So the participation number here is 19 out of 23. And then you convert, if you have to, you go into the proportion and convert that to something below 25 out of 25. And the whole number part, if that's greater than 75% of all the questions at the end of the semester, like say we have 120 questions, all right, by the end of the semester, and you've answered 90 of them correct, that's 75%. So you got a B on clicking in class, right? You get 4 bonus points. So the whole number is from bonus pointage, and the decimal part is for the participation party rate. Another question. Okay, let's keep going. We're going to talk about a little bit about molecules today. I'm going to give you some, this is ammonia. Here's another picture. This is an actual photograph. That one of ammonia was a model. This is actually using a special atomic force microscope. Those are actual benzene, hexagonal benzene rings, and they're covalently bonded. Very difficult photograph. That's an actual direct image of a set of 3 benzenes and a bunch of other things bonding. Here's vitamin C, ascorbic acid. So we're going to talk a little bit about molecules. Matter of fact, we already talked about this one on homework. Homework 9, the hexagonal protein molecule, which is my attempt to emulate nature and keep things fairly simple. So this one, this hexagonal molecule problem that you had to tackle, it's basically the same as one moving boxcar hooking up with 5 that are at rest. Because this molecule, the green delta molecule is 1 unit of mass, and the yellow H molecule is 5 units of mass. And I actually was very, very careful putting all this together. So it's basically the same as this interaction, except that you have different mass measuring regime, a different unit for measuring mass. Now, I made that up, molecular mass unit, MMU, but there is a real life unit of mass for things like molecules and atoms. It's called the atomic mass unit. And we'll talk about that in a second. But let's work out an example using your iClicker. And hopefully this is going to trot you through some of the basics, but in case you got tripped up on question 11, here it is. And we're going to do this one. The delta molecule slams into the H molecule at a velocity 12.3 meters per second. And just make a note to yourself, because you're going to need it eventually, that the mass of the delta molecule is 1 molecular mass unit, and the mass of the H molecule, the yellow job, is 5 molecular mass units. Okay? So, excuse me. So let's think about this. It's a boxcar going into 5 boxcars linked together, and they're at rest. So this collision, you're after the interaction, you're going to move off to the right at some new speed, and that's what your task was in this problem. So let's get at it step by step. Okay, so we're going to do several clicker questions here. Here's your first one. Okay, you should have go nitro. Initial speed is 12.3 meters per second. What's the momentum of the delta molecule? And hopefully this is cinchy. Have you been to Ave Maria University? Excellent. I've heard it's a good school. Does he like it down there? Yeah, it's good. How did they do in the hurricane last year, Maria and Irma? That's the one thing I don't like about Florida. Well, plus there's no mountains or anything, but these hurricanes, boy, they really tell you. All right, let me see what you guys are voting for. Oh my goodness. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 99 students. Let me click this. Okay. Yeah, the correct answer is 12 point. Boy, this thing is really going slow this morning. Okay, 12.3 MMU meters per second. Now, eventually these things are going to cancel out. So I could call these molecular mass units, I could call them Bob if I want. Because they cancel, in this problem anyways, they cancel out. All right, so let's do another question. Question 2, here it is. Slightly different. What is the momentum of the entire hex molecule? Now that's the light greenish yellow hexagon down at the bottom. And hopefully so the hex molecule in light greenish yellow is basically the H and the delta smushed together. Kind of like the Jello in space problem, the two blobs of Jello smushed together. And that was two boxcars coming at each other, different mass, and I think they were different mass, and different directions. The same philosophy as this. Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. I'm going to show you this one because it's actually... Here's the array of answers. So you can see that there's a spread between B, C, and D. All right, now B is 12, B is 12.3 MMU meters per second. C is 73.8 MMU meters per second. And D is none of the above. So we have to talk about that because the correct answer is actually 12.3. And the reason that it's 12.3, let me make sure I grade this. The reason it's 12.3 is conservation of momentum. The momentum of the delta particle comprises all the momentum of the entire interacting system. Because the other part of the interacting system, the H molecule, is at rest. So that's like 5 boxcars at rest. They have mass, but they don't have any momentum. Not yet. Now, after the interaction, all the momentum is going to be in the entire hex molecule, the hexagon pictured. But it's going to be more massive. It's got 6 times the mass of the delta molecule. All right. So you're going to move off at a slower speed. All right. V nu is going to be a little bit lower. All right, let's do another question. So if you, and most of you, only 24% of you got that correct. So I want you to make sure you make a note of it. That conservation of momentum in an interaction means that the momentum of everything going into the interaction is the same as the sum of all the momenta after the interaction. All right? Before the interaction, it's 12.3 with the delta molecule and a bunch of zeros, or a big zero for the H molecule, the yellow H molecule. But afterwards, all that 12.3 is concentrated in the hex molecule. It hasn't disappeared, it's just rearranged itself. All right, next question. Which equation connects conservation of momentum? I'm glad we're going over this because this is going to help you. Think about all 3 of these equations. Which one connects conservation of momentum and the definition of momentum after the interaction? Because remember, that's the key strategy. We worked on that on Thursday. After the interaction, conservation says you still have the same amount. It's just rearranged between, a different number of particles maybe, but it hasn't disappeared. So go ahead and make your choice. And let me. By the way, I'll make a comment later. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's now 102 people that voted, and I guess I saw a few more people come in than were here for the first question. But some of you might ask me, well, Dr. B, why don't I have 23 out of 23? And sometimes it's because you come in a little bit late. I've been last week, a couple weeks, Connor, I've been doing a lot of questions at the beginning of lecture. Sometimes I do them at the end, but if you come late and I'm doing them at the beginning of lecture, you're kind of SOL, at least for a few of the questions. And most of you got it right. Equation B is the correct answer. Now let's take a look at this. Go ahead and write it down if you haven't already got. Who voted for B? Raise your hand. Okay, good. Good. All right, so that's kind of interesting to me because you shouldn't be able to get the second question wrong if you got this one right. But most of you got this one right, even though most of you got the previous question wrong. And I'll just point one thing out here. 73.8 is a total juke. It's me multiplying the original momentum by 6. Okay, so you don't do that. All right? Now, if they were all moving at 12.3, then yes, you would do that. But that's not what you got here. So that's like a little bit of temptation to juke you out of place. But I didn't really, 75% of you got it right. And only 6 people got juked into equation C. Anyways, in equation B, take a look at this. There's your big string of boxcars. All right? As I said, the boxcar interaction is very helpful for understanding a whole lot of physics, including this molecular transformation process. This is kind of an idealized thing, but chemists and biologists and stuff, they want to know all about proteins and other complex molecules that are gigantic. We're going to talk about a really big one called Retina in a few minutes. But, thinking of it as a string of boxcars, yeah, it's not that bad. All right, and then over here, here's the conservation of momentum. That's the after. You have a string of 6 boxcars after the interaction, and conservation of momentum tells you that after the interaction, you still have 12.3 MMU meters per second. So you're good. Now all you got to do is solve this one. And don't forget, as I mentioned, you can see it here. Matter of fact, you can see it in all 3 of these equations, that the molecular mass units cancel. All right? So as I said, they don't, in this kind of a calculation where you're trying to figure out the speed and figure out where it's going and how soon it'll get there, which is, eventually what you need to do in problems of this kind, those mass units are going to cancel out. So, so you could have used kilograms, but then you got to use scientific notation and all that stuff, and it's kind of a what are those, s'mores? No. No, I've got my lunch up here, so I'm good. No, it's all right. It's good. I had a student, one of my top students a couple of years ago. She became the SI leader, but when she was the student, she would sit in like the front row, and almost every day she would bring a bag of Cheetos or something. And she would, and because it was right after lunch, so she would, like a 1:30 lecture, and so she would, and it always drew my attention. As soon as she opened it, like, who's got Cheetos? Who's got the Doritos? So, no, it's good. You're fine. Who figured out the speed? Anybody? Bueller? What do you got? 2.15? Okay. Oh, 2.05. Yeah, that's what I got. All right, so you could answer that. And yeah, I did. I forgot to add it in. That is the correct answer for that one. This is an example from homework 9. There really is one. You get it randomly, but 12.3 meters per second is one of them. Now, I want to go from that homework review, and we're going to start talking about retinal and other molecules. And retinal is a part of the rhodopsin molecule, which is in your eye, the retina of your eye. It's called retinal because it's a part of the retina of your eye. And this is the molecule that triggers your optic nerve. It responds to a photon of light. A photon is a particle of light, transfers some momentum and energy to the retinal molecule. The retinal molecule bends and then unbends. And when it does that, in response to the incoming photon, it then sends a message down the optic nerve into your brain. And there's zillions of retinal molecules in your retina. And that's how they work. And so I just love this one because everybody's got it. And it's something you can always think about. And it's pretty simple. It just bends and unbends. Now let's get down to some of the brass tacks of molecules. Instead of using MMU, which is kind of fakey, I made it up for homework. But there is a real atomic mass unit that scientists use. It's called the atomic mass unit, AMU. And sometimes you see it written down as a U. And this is the handy size for measuring atoms and molecules and stuff. So instead of using kilograms or even grams, which you're definitely allowed to do, scientists use atomic mass units. Like this tile for oxygen in the periodic table. The periodic table is a big array of all 100 and something elements stacked up in columns and rows. And everybody in the periodic table has an atomic mass unit. So it's approximately the mass of a single proton. And so hydrogen is about 1.00 AMU. And oxygen, oxygen is 8 protons and 8 neutrons in the nucleus. And the electrons are pretty shrimpy. They're about 2,000 times smaller than the mass of a proton and a neutron. The proton and the neutron are almost the same mass, very close. So oxygen is approximately 16, right? And retinal is about 284. Now go ahead and write that down. Retinal's got a bunch of atoms, a whole ton of atoms, and it's got a bunch of protons in each atom, and it's got a bunch of neutrons in each atom. And in an atom, the mass of an atom most of it is in the protons and neutrons in the nucleus. The electrons don't really contribute a whole lot. I mean, they contribute electrically in the chemical reactions and stuff. They're everything. You know, the protons don't really do much chemical reactions. They do nuclear reactions, but not chemical reactions. So most of the mass is in the nucleus. Anyway, so the momentum, P equals mv, if you have a hydrogen atom moving at 1.0 meters per second, well then, okay, the momentum is 1.0 AMU meters per second. That's kind of like our homework, but this is a real unit instead of a fakey Dr. B made up for homework unit, MMU. This is an AMU. And it's equivalent, you know, the atomic mass unit is equivalent to 1.66054 times 10 to the minus 27 kilograms. So yeah, if you want to measure atoms and stuff in kilograms, you're welcome to do it, but you're going to have to deal with scientific notation. And scientists, especially physicists, being lazy, almost as lazy as mathematicians in the math department, we like to have, you know, nice round numbers. So we use the AMU. If we're working on atoms, we use AMU. If we're working on stars and galaxies, we use kilograms. You know, we don't have anything else. We don't have any big, huge astrophysical size unit. Actually, we do. I take that back. You know what we do for stars? We rate the mass of a star or a galaxy in terms of solar mass units. We can do that. You know, in other words, a big star like Sirius is maybe 2 solar masses, or 2.5 solar, or the big star Betelgeuse, big red star in Orion. And Orion is up in the sky early in the morning right now. And it's one of the most beautiful constellations. And it's got a big red star in there called Betelgeuse. And as I recall, Betelgeuse is quite a bit bigger than the sun. So it's got, you know, some number of solar mass units. Anyways, for molecules and atoms and stuff. Oxygen, going at 1 meter per second. 16.0 AMU meter per second. Retinal, going at 1 meter per second. Getting a bunch of bips from a bunch of photons of various sizes, and if it's going 1 meter per second, its momentum is 284 AMU meters per second. All right? And so just remember this. The AMU is 1.66054. You're never going to have to calculate with that number, but I mean, if you feel like writing it down, just to reinforce the fact that it's really small, it's about the mass of a proton, you know, that's good. Yeah, Connor.
So where is a molecule moving to?
It's moving in the same direction as the photon that interacts with it. You know, the photon is going to surrender its momentum and energy to the atom or molecule. And so just like the Hex molecule, whatever momentum the photon had, the Hex molecules or the retinal molecule is going to have. Okay? So if the photon comes in from left to right, the molecule that absorbs it's going to be going for, unless it hits it off center, then it's going to cause it to move off in a certain direction and spin. So, that's also possible, because it's an oblong. Retinal is long. And retinal, if you hit it right, will bend and unbend. That's another mode of absorbing and releasing energy. So, but for, a simple collision, yeah, the same direction. Now, I've got another clicker question for you. And this one, I want you to read it really carefully. It's about retinal and a photon delivering some AMU meter per second of momentum into the retinal molecule. Here we go. A photon delivers delta P 71.0 AMU meter per second of pure momentum to a retinal molecule. So what's V nu for the retinal molecule? And the photon is massless. So unlike the H and the delta, the delta adds the 6th unit of mass to the hex molecule in the homework. Momentum, the photon has momentum, but it has 0 mass. So the mass of the boxcars is still 284 after this interaction. All right, so type in your answer and think. Think, think, think. Boxcars, momentum, impulse, delta P. And the force that mediates this is the electromagnetic force, incredibly fast delta T's. So we're going to kind of sidestep that. But we're going to think in terms of momentum and momentum transfer. Good. I see you guys coaching each other. Remember, in lecture, you can always do that. You can always talk to somebody that's sitting next to you or behind you or something like that. Unless they move over to a different spot. Khalid. You didn't even notice what I was giving him the business. 30 seconds. $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Yeah, we have a little bit of a most of you voted for B, 55%. That's a majority. 28% voted for A, and a few dribs and drabs C, D, and E. Let's work it out. Okay, so delta P is P subscript F minus P subscript I. Now, P subscript I is 0 because the retinal is at rest. Okay? And so that means whatever PF is, it comes from delta P. And delta P is 71. So we'll assume it's 71 positive going to the right, just for bookkeeping purposes. All right. So P subscript F for the retinal molecule is going to be 71.0 AMU meters per second, right? Because that's what the photon delivers. The photon doesn't deliver any mass. It does deliver momentum and energy. And in terms of momentum, yeah. So there's your final momentum of Retina. So it's poking off to the right with a momentum of 71. Now, definition of momentum, P equals mv says, whatever the momentum is, it's 284 AMUs times V final, or V new, in the terminology we were using last week. Right? So there's my conservation of momentum on the left and my definition of momentum on the right. And now all you got to do is divide both sides by 284. Okay, so that's this step. And you can see that this one works out. You know, I use nice round numbers because secretly I didn't want you guys to be tripped up too badly. 0.250 meters per second. So it's kind of poking along. You know, the photon's going at the speed of light, has a certain amount of momentum, and the retinal molecule's pretty big, but you can measure that, 0.25. That's like half a mile an hour. Yeah, it's about half a mile an hour, so it's kind of poking along. It's kind of dawdling. So, and here's the cancelizations. You can cancel up here in the middle equation block, or you can cancel down here in the third equation block in that quotient. But whatever you do, your answer is going to be 0.250. So that's the correct answer there. All right. And I'm emphasizing atomic mass units and the fact that they cancel because I want you guys to be able to tackle questions about molecules on exam 2 and not get too tripped up on how small they are. If you stay to AMUs, you're going to be good. It's going to be fairly easy. You won't have to do a whole lot of scientific notation. Now, eventually, we're going to have to deal with scientific notation. We can't dodge it forever, but for right now, we're going to try to dodge it that way. Last time, we talked about coordinates and dimensions in space-time. And, you know, in order to make our calculations, you know, of velocities and curvatures and distances and stuff for various events, you have to have some kind of a coordinate system. All right? And the classical, you know, like Einstein's definition of coordinates was a fixed object like a ruler, a meter stick, you know, that, you know, you could use as a coordinate. But, you know, it's possible to have what we call curvilinear coordinates, like spherical coordinates. You know, latitude and longitude, those are curvilinear. You know, they're curvaceous, you know, because the surface of the Earth is a curved spherical surface. All right. But, you know, most of the time we're going to be, in X, Y, and Z rectangular coordinates, rectilinear coordinates. Now, Einstein says that we have to use time as more than just a bookkeeping tool. You know, for Isaac Newton, you know, Isaac Newton thought about time as well, but for him it really was pretty much a marker. And even in Einstein's theory of relativity, you know, I was just reading last night about it, every trajectory of an object, we model time as a bookkeeping device along the trajectory. You know, every different units of time. But for us, we have to give it dimensional status as the fourth dimension. And we have to think of the universe itself as a space-time. And so we have to treat time as if it were an X, Y, or Z coordinate as much as possible. So that's one of the lessons that not Sir Isaac Newton, but Albert Einstein shared and developed. And we talked about that last time. We talked about how the space-time position of an object requires 4 numbers: the time, the x, the y, and the z coordinates. All right? And that those are the 4 dimensions of space-time. And that therefore the dynamical quantity that corresponds to that is the energy and then the 3 components of the momentum: the x momentum, the y momentum, and the z momentum, if there's any. Now, most of the time we're working in 1 dimension. So py and pz are 0. And we're only, like the box cars. That's x-axis only. But if we were thinking about a baseball, then we'd have px and py, and maybe even pz if it had a little bit of spin on it. Because a baseball, you'll hit it toward the outfielder, towards the left fielder, and it goes along the left field line, and it curves to the left and out of fair territory. So 3 dimensions sometimes for something like that. Now, as I said, we want to treat time as much as we can like any of the other 3 dimensions. So here's what we're going to do. We're going to make a simple space-time graph. All right, now go ahead and write a vertical and a horizontal axis, and go ahead and label the x-axis, the horizontal axis, the x-axis. Now, what we're going to do is make this axis, it's going to be measured in meters because this is going to be like graph paper coordinates, but instead of calling it the time axis, we're going to multiply by the speed of light, c. Now, c times any time is a distance, like light years, So this is like your light years axis. We would call it the temporal axis. So here's, so mark it down as CT. And now we could do Pythagorean theorem as much as we like. We're measured in light years for our unit, the size of our blocks, or maybe light seconds. But yeah, you can do it. It's possible to do Pythagorean theorem and everything else. Now, I want you to draw some horizontal graph paper lines, and I've got 4 of them, all right, equally spaced. And those are going to, they're equally spaced, so there's the same c delta t between each of them. All right, so go ahead and, c delta t, 2c delta t, 3c delta t. The last one is 4c delta t's above time t equals 0, ct equals 0. Now, one of our laws of physics, Newton's second law, it is restatable as the impulse formula. Right? So F delta T equals delta P. And what that means is if C delta T on this equation, on this space-time diagram, if those are all the same intervals, going upward, then the delta P is going to be the same. So every increment of C delta T that you go upward into time, you're gaining or losing, depending on your force, equal amounts of delta P. So the temporal scale, C delta T's, give us an adequate, or we have a law of physics that we've already figured out, Newton's second law, restated as the impulse formula, and it is in perfect position to understand all those horizontal lines on the CT axis. The momentum would be the same, the delta P would be the same, at each level of the CT axis, if the force was constant. It's like mg, or something like that. All right, so that's pretty good. Now, I want you to draw another 4 lines horizontally. All right, here we go. And I've spaced mine out really carefully, and you do your best so that you have squares if you can. And let's just call this the spatial partition, delta x. And so our logical question is, all right, Newton's in space-time, in 4-dimensional space-time, the impulse formula is made for the c delta t's, going up or down on the vertical axis. Is there some law of physics that is equally kosher going left or right with equal delta x's? So if you partition your study spatially with delta x's instead of temporally with c delta t's, what law is there that exists in nature that makes sense of the delta x's the way that the impulse law makes sense of the c delta t's? Connor.
I don't really understand what we're talking about. As far as what the delta x's represent, and
Well, the delta x's represent a certain distance. We're making them all the same. So basically what we're saying is our graph paper can be divided up spatially, or it can be divided up temporally, meaning along the CT axis. Temporal means time, tempus fugit. Okay? So when I say temporal axis, I mean the CT axis. Okay? And along the CT axis, equal delta t's equal c delta t's correspond to the way that the impulse formula is set up. So it's ready-made. And we didn't know this. I mean, we knew it. We knew that F delta t was equal to delta p. But not until Einstein started thinking in terms of 4-dimensional space-time did anybody, make this kind of connection. So there ought to be some law, maybe not Newton's second law, but something that, if we do the other, kind of lines on our graph paper, there should be some law, maybe not F equals ma, F delta t equals delta p, but maybe something else. And of course, the reason that I'm bringing that up is because I know that there is. Question?
Is this going to be used to measure space-time? And what is this going to be used to measure? Is it going to be distances in specific time intervals, or?
F delta t equals delta p. The delta p's are all the second, third, and fourth slot in that column on the right. The energies, so we got to do our dynamics using that energy momentum stack, that energy momentum vector. If we want to map something out on graph paper in 4 dimensions, we got to use time, x, y, and z. All right? To do all the physics and stuff, Newton's second law lives nicely and encodes nicely down here. Where's my cursor? Come on, baby. Right down here. Newton's third law, or his second law, excuse me. F delta t equals delta p slots in right down in here. But what about this baby up here? That's what I'm talking about. All right, and that's what we're going to get to here. So let me trot through these again. Come on, baby. Here we go. Okay, so there's my temporal partition equals c delta t's. Here's my spatial partition equal delta x's. And the question being, what law is coherent and controls that first slot in the dynamical energy momentum tensor. And the question, and this is the law right here. It's the work formula. F delta X equals delta K E, delta kinetic energy. And the change in kinetic energy is defined as work. Kinetic energy is defined as 1/2 mv squared. Now remember, Connor, momentum is mv. Kinetic energy, now this is the energy that we're going to put in the very top slot of that dynamical vector, a couple pages back. And this is the one that's going to make sense four-dimensionally. So, Red Shirt Man, what was your first name again? Liam. Liam, this is going to, energy is going to, all the laws of energy and stuff are going to live in the top part of that energy momentum vector that I had stacked up, a couple slides ago. And this is the first energy formula. Now, there's a few others, and we're going to develop one more today. But in terms of, does this look like the impulse law? Hopefully it does. F delta something equals delta something else? Yeah. But it's not F delta T, it's F delta X. And it's not delta P momentum, it's delta KE, 1/2 mv squared. And this is how it all fits together. Now, why that happens, nobody knows. But it does work out nicely. Why did God make the world a four-dimensional space-time? We don't know. We're going to have to ask him one of these days. But it does work out this way. Connor. F delta X equals delta kinetic energy. Yeah, F delta X is over here. Okay? And we call it the work. And hey, you guys, capital W here means work, not weight. We have that weight force, W equals mg. Okay, so you have to read the context carefully. And, and you'll know whether you're talking work or weight force. Colin.
Well, a bit lost as to what CT is and where it came from. Can you go more in depth into that?
CT? Yeah. That's a couple slides ago. CT, we use CT to label instead of making it just a t-axis, a time axis, like the velocity graphs. We had the time axis horizontally and the velocity axis vertically. Remember that? And we didn't do anything with that. We just left it as the t-axis, the time axis. But in order to measure distances in space, if time really is the fourth dimension, we want to treat it, for instance, as if we're going to measure a distance with time. Now, the only way to do that consistently is to have some speed times time. And the speed that Einstein decided to use was c. Because c is a constant of nature, the speed of light. And so it's just like what astronomers do, really. They measure the universe or the distance to stars, the breadth of a galaxy in light years. The speed of light times 1 year. 365 times 24 times 60 times 60 seconds times the speed of light is a light year. All right? So it's basically what we're doing on that space-time diagram. And then on that diagram, you could calculate, a squared plus b squared equals c squared. All right? And so that's why we do it. All right? To make instead, you may remember when we were talking about the velocity graph, I said, well, you can't really say that the area, it's square meters because one dimension is meters per second, the height. And one is time. That's not meters either. But the area is meters. That's how we, interpret the area for the velocity graph. So, Okay? So it's, don't feel bad that it's a little bit new to you to think about, and because everybody has to deal with it. Everybody has to kind of think differently about time and stuff. That's the whole thing with relativity and the four-dimensional space-time. Anyways, let's keep going with this. Now, hopefully you see the resemblance to the impulse formula here. And impulse formula and the work formula, Connor, that's what we got here. This is the work formula. F delta x equals delta KE. They form a pair. They're perfectly matched. Now, the metric unit of work is called the joule. We don't have a name for the metric unit of momentum. We just have kilogram meter per second. But for energy, yes, we have the joule. And joule is the name of a British scientist from the 1800s that figured out a lot of energy concepts. So for instance, if you take a 1 kilogram object and it's moving at 1 meter per second, its kinetic energy is 1/2 times 1.00 kilograms times 1.00 meters per second quantity squared. And so your unit is kilogram meter squared per second squared, and in fundamental units. Okay, so the metric system, the things that we can measure are kilograms, meters, and seconds. Okay, and this particular combination is known as a joule. Now, kilogram meter per second squared, what's kilogram meter per second squared? Remember what that is? What's a special name for that? It's a Newton, all right? So here's another thing. 1 Newton meter is also the same as a joule. So 1.00 joule, 1.00 kilogram meter squared per second squared, or just, 1 Newton meter. Now, if any of you have ever had your own hunting rifle or any kind of a firearm and you do your own loading or you buy ammunition, a lot of times they'll rate the ammunition in foot-pounds of kinetic energy. That's the British system, the English system, feet, distance, pound, force. Okay, it's kind of archaic. We don't use it much in science, but ammunition, so like police will say, well, that's 500 foot-pounds of kinetic energy for this ammo and 600 for this other kind of ammo. Just depends on how much gunpowder it has. It's basically rating how much gunpowder you have and how much speed it delivers to your bullet. Anyway, so the Newton meter. So when we're doing calculations with the work formula and stuff, and we want to do some cancellations, you guys, sometimes we're going to want to have kilogram meter squared per second squared if we want to cancel kilograms. If we want to cancel a force, some number of newtons, left and right, or top and bottom, in a quotient, we'll change the energy into Newton meters. And then you can, then you're left with meters, right? But otherwise, you just write it down as capital J for joules, and you're good. Now, and we're going to do some calculations of all this stuff this week. Let's do another important energy quantity. And Liam, this is another thing that can find its way up into that top part of the energy momentum vector. It's called potential energy. Right? So let's think about a baseball. The baseball goes up in the air and it loses kinetic energy on the way up, slows down. 1/2 mv squared is going to be smaller on the way up because v is smaller. It's upward speed. Okay? And if we define gravitational potential energy in this way as the opposite of F delta x, You know, the change in kinetic energy is F delta X, or minus F delta Y if you're in free fall. The weight force being mg. Then, and here's the formula for gravitational potential energy at the surface of the Earth, minus mg, that's the weight force, times delta y. And that is going to measure, it's basically the lost kinetic energy. All right? So as the object goes up, it loses kinetic energy, and it goes into gravitational potential energy. So here's how and so the way that we would describe that is the trajectory of a baseball. We would describe it as an exchange of energies. You know, we already know about exchanging momenta. We've done a bunch of that with molecules and stuff. Exchange of energies, yeah. It's for every joule of kinetic energy lost on the way up, it goes into a joule of potential energy. And vice versa. If you start at the top, you know, if you're at the top of the Empire State Building, you have a certain amount of potential energy. You're holding your water balloon. Well, you wouldn't want to hold a water balloon at the top of the Empire State Building. But, you know, the top of the library, you're holding a balloon over there, and it's got a certain amount, but it's not going anywhere, so it doesn't have any kinetic energy. So you're up there holding it, and you're waiting for somebody to walk underneath you, and then, you know, like your roommate or something, and drop it on them. And you don't have any kinetic energy, but you have a ton of potential energy. All right? And that's measured by minus mg delta y. The mass of the water balloon, g, 9.8. And then delta y, the height of the building. You know, the height of how far you are above the sidewalk. Now here's the other cool thing. The total energy, capital E, defined as the sum of the kinetic and the potential, that's a constant. Because what the kinetic energy loses, potential energy gains on the way up. On the way down, what potential energy loses, kinetic energy gains on the way down. It gets faster. All right? So this formula here, E equals KE plus GPE, that, my wonderful students, is the conservation of total mechanical energy. If we model the trajectory of the baseball or any other gravitational arc as an exchange of energies, potential and kinetic, this is always going to be true. You're always going to have some number of kinetic energy. Just like in momentum, we have some number of kilogram meters per second or AMU meters per second, and it just maybe transfers or rearranges. Same thing here. Now, we're going to do a little bit of a workout here in the last 5-10 minutes on the energy levels in Earth's gravitational field, kind of like these guys. All right. Now, here's our example. Very, very simple. And you're going to have a clicker question here in a second, so don't put your get your clicker back out. Now, here's what we're going to do. We're going to take a 2-liter bottle of Mountain Dew. So that's 2 kilograms. It's basically water. And ignore the mass of the bottle. That's pretty small. All right, we're going to take it up to 10 meters up and hold it. All right, so go ahead and make see that? Your vertical partition. There's your spatial partition. And up at 10 meters, you got 0 joules because you're at rest. 0 joules of kinetic. And now what we got to do is figure out mg delta y. All right, so 2 kilograms times 10 meters times 9.8. All right, so let's figure that out. Next question, here we go. minus mg delta y. What is GPE of a 2 kilogram bottle of Mountain Dew at 10 meters altitude? So this is 10 meters above the sidewalk. And go ahead and vote. And hopefully this one's cinchy. Minus mg delta y. So, and in this one, delta y is positive because you've raised it up to 10 meters. G is negative 9.8. And then you have a minus sign in the front. So your number here is going to be positive something point something joules. So minus 2 kilograms times minus 9.8 times 10 meters of skyward lift up. And you guys are doing good. 30 seconds. $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. Yeah, you guys are geniuses. Pretty much. 196. A couple of you got tripped up, but 95% of you got it right. All right, so go ahead to your table and label this one in there. Question?
Why is the answer positive versus negative?
The equation is minus mg delta y. Okay, so your delta is from ground level up to 10 meters. So that's a positive. G is negative 9.8 in this equation. And then you have 2 kilograms for the mass of the Mountain Dew. And then a minus sign in front of that. So you have 2 minus signs in there. So minus times minus is positive. Okay? And that's so you guys, using that formula, you have to be really careful with your minus signs. Okay? But you know, Adriana, if you can do the same thing, minus mg delta y, for a negative, okay? If delta y is, you know, if you start up at, you know, if the top of your building is 0 and you let it fall 10 meters, then delta y is negative and you've lost potential energy. So the potential energy is 196 joules less by the time it's, and matter of fact, let's do that. Down at any level. Before we do that, total energy, 196. Go ahead and write that out. And so we're going to have total energy, 196 at every level. And just before impact, here we go. We've lost all the potential. We've lost 196 because now, after that trajectory, you've dropped minus 10. All right, and so you've got a goose egg down there for gravitational, but it's all kinetic at that point. All right? And if you think about it, this is also, the work formula is also a very slick way, easy way of figuring out a stopping distance. So unlike the problem with the little shrimpy kid at the ice skating rink, this is the way to do it. Now, he's not in free fall or anything, but he's got a frictional force. Now, anyways, let's get back to this table. You have energy, 196, down there too. Total mechanical energy, 196 joules. And you can see here that it's exchanged. All the potential at, when you started has been converted to kinetic by the time just before it hits. All right? And so if you look at the table, go ahead and make yourself a little table. You've got 196 all the way down. At any altitude you want. You might have different mixture of kinetic and potential, but the total mechanical energy, that fourth column over, ding, 196. So that's ditto marks all the way down, basically. If you can find the total energy at any elevation, or if it's given to you at any elevation, just write ditto marks all the way down. All right? And then go, figure out, up at the top where it starts at rest. Or down at the bottom when it reaches maximum kinetic and zero potential. And so your homework number 10, I'm going to give you a couple little practice problems with a table like this. And I think I might not use the Mountain Dew, but something else. And just a little bit of practice on that. So that'll be due on Thursday. Let's dismiss a few minutes early, and I'll see you then.